Hello, Health Science 4502. This is Professor Van Dyke, and this is the lecture for Wednesday, September 9th. I hope everyone had a wonderful Labor Day. And we're going to be talking about noise for this lecture. And as you probably noticed, with regard to the syllabus, we're kind of jumping around a little bit. It's not going to matter. We have plenty of time to cover this material. So there really isn't going to be any rush to get through a lot of this stuff. With the semester system, we've had some changes, and certainly with regard to this uh, process with coronavirus, it really is an interesting process to try to have labs that are really meaningful for my classes. I remember when I took this course quite some time ago, we would actually go out and try to measure noises around Cal State with actual dosimeters and um, other noise sampling devices that we actually had at Cal State. But I think actually this may end up being a little bit better. I'm hoping that we can get some positive interaction in regard to this, and would encourage everyone to be a part of this process that is really interesting and challenging and fascinating all at the same time. So we're going to go ahead and jump into it. There's a lot of slides. For the most part, I'm going to very cursorily cover this information. We're not going to get too in depth with it. So I want you to kind of be able to read it over. There's not a lot that you can really manually calculate with regard to noise, but we're going to kind of have a little bit of fun and see if we can make this interesting and good learning experience for you for being able to sample noise. And for the most part, with noise sampling, you have units that are going to be calculating everything for you. You're going to have audiometry devices. This is, of course, when you're working in the occupational setting. You're going to have dosimeters that individuals can wear throughout the day that will give you the time-weighted averages. You'll have all kinds of helpful tools that will allow you to properly manage noise exposure in workplaces. So kind of keep that in mind. A lot of these slides are going to have some theory to them, but again, there's not a lot of stuff that you would actually have to manually calculate in regard to noise processes, making sure that your workers are protected from noise. So we're going to go ahead and jump right into it. This is Lecture 3. Obviously the date on slide 1 is not correct, but we're going to go ahead and move right through this. So if you're working from your textbook, this is slide 2. This is going to be the NIMS textbook, pages 205 through 220. And again, if you don't have the book, it's definitely not an issue. I really encourage you to learn from the slides and do what you need to do in regard to refining some information. If you have questions, make sure and send those questions to me. So slide 3, why is noise control important? Hearing loss is huge in working environments, especially when you're working with things like presses, um, uh, large mechanical moving parts. These things can be very noisy, and certainly when you go to an airport or places like this where there's a lot of sound on the tarmac, you'll notice that everyone is well protected with personal protective equipment. But roughly 2 million people between the ages of 50-59 have noticeable hearing loss, and about 14% of workers are exposed to above 90 decibels. So dBA is decibels. A is primarily what the ear, the human ear hears. They make some variations for that, but just understand that when we say dBA, normally we're just talking about decibels that would affect and are part of the normal hearing process for the human. So they certainly, noise control is important because it will mask wanted sounds and speech it. And so if, like say for instance, if you're in class and someone sitting right next to you is talking relentlessly, you'll notice that it's harder to hear the professor. So there are the unwanted sounds that will mask the desire to hear the things that you need to hear, like possibly verbal instructions that someone may give you. And then there's worker fatigue. You know that if you've ever tried to sleep through the night with a dog barking next door, how challenging that can be. So there's a lot of fatigue associated with noise itself, including being in the working environment. You hear this loud sound consistently, it can physically drain you, and it can be very annoying as well. So there's an annoyance factor in regard to noise control being very important. So you want to have this ability to work in a place that's not going to physically drain you and annoy you from all the unwanted sounds. Slide 4. This is in regard to the properties of sound. You've probably seen these in your physics courses that you took. So rapid pressure variations in regard to sound waves. You have the frequency, which is marked as F. It's hertz or cycles per second. And then you have the wavelength, which is feet or meters in one cycle. And then the velocity of sound, which is very different if you're traveling if you're traveling through air or water. You'll notice that through air it's approximately 344 meters per second, where with water it's closer to 4,000 meters per second at 3,962. These would probably be the kind of questions that I would have in regard to making test questions. So it's going to be a little bit challenging, but certainly we'll do our best to make some fairly easy questions for you to be able to get those correct on the exams. With slide 5, you have a sound wave. So this is basically what we were talking about with regard to wavelength. You can see a wavelength here, and the distance is one wavelength essentially with amplitude. So this is going to be frequency, amplitude, and wavelength of a sound wave represented on a graphic formula. The ear itself, this is slide 6. We have the structure of the ear, which is very important because when you start having damage, these are the things that are going to really have issues. So with the structure of the ear, you're going to have the outer ear, which is the auditory canal, and the tympanic membrane. We call this the eardrum. And then with the middle ear, you're going to have the malleus, the incus, and the stapes. These are the actual bones that contact and allow you to hear sound. And then you have the inner ear, which is the cochlea and the organ of Corti. So if you've taken anatomy, physiology, you have intimate knowledge of this, but really not something that I'm going to have you label on an exam. So this is really more just information that you're familiar with these things, the malleus, incus, and the stapes, what they actually do roughly look like. But that essentially these are going to be those bones in the middle ear. On to slide 7. This is a graphic image of what we had just discussed. So this is a nice photograph of cutaway diagram of what these things actually look like. And then slide 8 is going to be transmission of vibrations from the eardrum through the cochlea. So again, you're going to have a chance to look at this. Section 2 is the ossicles. And then as the waves travel around and in through that cochlear image here that you see on slide 8. So again, just really more of a graphic image that you can look at, but nothing that we're actually going to make you memorize. So with slide 9, you do have forms of hearing loss in regard to conductive hearing loss and sensorineural hearing loss. So with conductive hearing loss is the impairment of sound transmission before it actually reaches the inner ear, and this can be due to a number of things like infections. If you have a bad infection, that's going to definitely generate conductive hearing loss, excessive earwax, or even damage to the eardrum itself. These are going to provide someone with conductive hearing loss, which can be very detrimental. And then with sensorineural hearing loss, this is the impairment of the inner ear components. So as you know, with sensory components, there's the hair cells in the cochlea can be missing or damaged. There is a picture on NIMS on page 210, but you can also find these if you go to just Google image and you search these things. You can find some really good image of these hair cells. So as you know, with the hair cells, they're very important in regard to doing a number of things, including allowing you to know which side is up essentially, but certainly can have a lot of factors associated with hearing loss. And then there's the neural component for hearing loss, which can be a cochlear nerve to the brain. So the cochlear nerve is going to allow your brain to understand that you are hearing things and process those things through that nerve. And if that is damaged, you can really experience some extraordinary hearing loss. So on to slide 10. The difference between the two is that conductive hearing loss is often reversible. It can be fixed, so you can remove the earwax, you can get rid of the ear infection, you can repair damage to the tympanic membrane, but usually that is so damage to the eardrum is usually going to have some surgery done, whereas sensorineural hearing loss is typically going to be irreversible. It's not something that you can fix, and really is one of the reasons that we want to focus on making sure that people are protected using PPE if they're exposed to anything that is greater than 85 and 90 decibels. So terms you should know, and definitely these are things that I want you to kind of understand. With noise-induced hearing loss, NIHL, this is any hearing loss resulting from excessive exposure to noise. It doesn't have to be occupational, so NIHL can certainly be going to a loud concert or going to a firing range and shooting a gun. And then there's proboscis, hearing loss associated with advanced age. Certainly something that we do tend to notice, but certainly not something that everyone experiences. Then we have tinnitus, which is the last term here, which is ringing in the ear due to traumatic exposure to sound, to loud noises. And tinnitus, just kind of an interesting little short story here. So everybody knows who Captain Kirk is. This is William Shatner from Star Wars. Oh my gosh, I'm sorry. Star Trek. Sorry, I've been watching Mandalorian. So Captain Kirk, William Shatner, was on stage, and he was involved in an exposure to a large amount of sound that gave him tinnitus when he was filming Star Trek. And he developed tinnitus, which is ringing in the ear, and it was so severe over a number of years of his life that he actually contemplated suicide because tinnitus was such a horrible thing for him to have to experience. And this was from pyrotechnics that were placed too closely to him, that he wasn't protected and shielded from these things, and because of that he developed tinnitus, which was very challenging for him to deal with. On to slide 12. Here are some examples of loud environments. Certainly you see the tarmac on the lower left corner, very loud. Gun range. If you've ever had a firearm that is discharged close to you, you know that tinnitus, temporary tinnitus, can be very common from that. And you have a concert on the top right, certainly a very loud environment. Slide 13 shows some audiograms showing conductive hearing loss. You can kind of check that out. Slide 14 is audiogram showing sensorineural hearing loss, and you can see that really some very interesting things occur right around 2,000, 3,000 hertz. Slide 15 is a measurement of sound. So as you remember, sound pressure is measured in micropascals. Threshold for hearing is 20 micropascals. Sound pressure level, the root means square average. I'm not going to make you calculate sound pressure, but it's essentially 20 log P over P naught in units of decibels. So one of the things that's interesting with this measurement of sound, if you double the distance, you essentially are going to reduce by 6 decibels, and we'll chat a little bit about that because this could be a part of what you get a chance to do for the lab for this. That doubling of the distance is going to reduce by 6 decibels, and you can see if this is true. And this is going to be in a free open field with no interference. On to 16. Again, dBA is when we talk about noise regulations, measurements, we always refer to the A weighted decibels, which is dBA. So A is weighted because it's the most representative of how the human ear hears sound. So you're going to see dBA. We're going to be discussing dBA, but usually when you see dBA, I'm just going to call it decibels. 17 is a graph from Wikipedia that shows gain in decibels. and it's going to have the dBA is going to be shown in blue here. But again, this is not the kind of thing that I'm going to be testing you on. It's really just more for you to be able to take a look at it, go, okay, so this is roughly how the human ear hears things, where dBB, dBC, and dBD are very different from how the human ear processes sound. Again, slide 18 refers to the 6 decibel rule. And as you remember, with decibels, with noise, with sound, the decibel scale is exponential, very much like the Richter scale is. So you're going to have exponential increases in sound as you go from 85 to 90 decibels. It's not a true additive scale. So sound pressure levels can be calculated as sound pressure level 20 is going to be equal to 20 log power 10, and then P over P naught. So P naught is the reference threshold pressure at 20 micropascals. And again, I'm not gonna have you calculating these things, because I find that it's better that you work with a decibel meter, and you take some notice on how these things actually work, and we'll talk a little bit about that with the lab. So typical dBA, decibel weighted sound levels. So you see some of these things, shouting, lawnmowers, loud lawnmower in an operator's ear is about 90 decibels, which is the as you remember, this is the OSHA federal guideline for noise exposure, is that you're at 90 dB, and then Cal OSHA does have some additional time-weighted averages that bring it down to 85. So 85 is traditionally understood as the noise exposure for Cal OSHA, where 90 decibels is the federal level. On to slide 21. Speech communication in a noisy environment. So you can see, when you have at 3.3 feet, you're going to have someone that's essentially shouting, and that's going to be at about the action level, which is 85 decibels. So if someone is shouting at you at 3.3 feet away, this is a very noisy environment, and it is almost to the level where you'd have to start taking action. 22 is combining sound levels. So the equation for adding sound pressure levels is shown here, and can be a challenge to calculate it. But again, this is not the kind of thing that I'm going to have you do. But usually, if you're working in a working environment, you're trying to get an idea of the noise in that area. That audiometric device for recording decibel exposure is going to give you those answers with the noises combined. So simple rule for adding decibels, and again, this is really an easier way to do this. So if there's a difference in 0 to 1 decibels, you're going to add to the higher level 3 decibels. This is generally going to be if you're adding decibel, two sound sources together. And so if you wanted to know, okay, I'm adding a lawnmower to a person screaming in my face at 3.3 meters. You're adding the two of those things together. You're going to take the difference in decibels, and you'll add essentially, if it's 0 to 1 difference in decibels or greater than 10, you can see the difference here. So if it's greater than 10, if the difference in decibels is greater than 10, obviously adding to the higher level of 0 decibels is going to have no change or no effect on that, because essentially that lower decibel recording is not going to be heard over this greater difference of 10 in regard to the decibels. I hope that makes sense. So if you're essentially, if you're going to be adding decibels of two sound sources, and one's 90 decibels and one's 5 decibels, the difference is greater than 10, so you're not going to be adding anything to that. So this is a simple way of adding decibels together. Question 24. This is going to be analysis of noise. And when you look at this here, so sound level meters, SLMs, are approved through ANSI and OSHA. and can be fairly effective. They work pretty decent, but you can also use octave band analysis and noise dosimeters. So OSHA wants you to go as close to the full shift as possible when you're measuring sound with a 5 decibel exchange rate. So really, what you really need to take from this is that with OSHA, if you're doing noise dosimetry, you want to really calculate the whole process. So if someone's there for 8 hours, you want that noise dosimeter on the individual for that 8-hour shift. And that's really what I want you to focus on. Don't focus on these exchange rates. Make sure and focus on the fact that if you're doing noise dosimetry, that you really want someone wearing this device for 8 hours if they're doing an 8-hour shift, 10 hours if they're doing a 10-hour shift. Slide 25. This was some Mike's takeaways that we got from Mike Wynn, who also teaches this course as well. Sound level meter is used for real-time measurements. It's best to figure out how noisy an area or a piece of equipment is, and that certainly can be done very easily with the sound level meter. A noise dosimeter is typically used to take a measurement over time. So this is going to be where someone is going to wear this device or carry it around with them for, potentially 8 hours for their whole shift. And you have to calibrate an SLM before every use. Use an acoustic calibrator, and an acoustic calibrator is going to produce an exact number of decibels consistently, so it allows you to take these SLMs and make sure that they're working properly before you go out and start using them. And this was something like with the lab for this class, it's going to be a little bit challenging because obviously you're not going to have an acoustic calibrator, but they do have them at Cal State. So if you ever get back up on campus, you can check these things out. Slide 26. This is a sound level meter, and as you can see, it's pretty straightforward. You turn the thing on, you hold it up, you check it out and see if it's working with the calibrator, and then you can go out and actually start utilizing it in the field. Type 1 on slide 27. This is an integrated sound level meter, which is a little bit more sensitive. We also have these at Cal State as well, and this is going to let you know what the sound level is in any given location. Slide 28 is a dosimeter, so you can take a look at this. And again, these things are kind of the ideal equipment if you're working in a very noisy environment, that an individual will wear this for their entire shift, and it will give you the dosimetry associated with the work that they're doing. Slide 29 is the acoustic calibrator, and again, this is going to produce sound at 114 decibels, so it allows you to test it in a location that's a little more quiet, and gives you a truer test to verify that in fact your noise calibration is going to be appropriate, that it's going to show that it's at 114 decibels before you take out these sound level meters. So you want to know that your sound level meter is working before you actually go out. Slide 30 is going to show the OSHA permissible exposure levels. So as you remember, PELs are something that we do have to follow, unlike RELs, recommended exposure levels. So with the PELs, federal and Cal, so you see duration at 8 hours, one full workday is 90. But as you begin to make adjustments to the duration, so if you're working 4 hours, your sound level is at closer to 95. So things do change depending on the number of hours you can work. So as you remember, this is a time-weighted average, which is really important to take into consideration. On to slide 31, which is the ACGIH threshold limit values. So as you see here with the duration, it's 8-hour shift is at 85 decibels. And then as you cut it down from 488, so you start to see these changes. So again, with slide 31 is recommendations like RELs, and slide 30 is PELs, which you have to actually follow. And then on to slide 32. Slide 32 is an expanded version of the OSHA noise table. So this is just kind of gives you a little bit of a better understanding of where you are based on time-weighted averages. So again, everything is associated with time-weighted averages. You can work for 8 hours and be exposed to greater than 90 decibels, but for the remainder of your shift, for maybe half of that shift, you have to be in an area that is below those 90 decibel thresholds in accordance with federal OSHA standards. On to 33. So we talk about some of the takeaways. So using a smaller exchange rate results in more conservative interpretation. So OSHA, you can be exposed to 100 decibels for 2 hours, where with ACGIH you're looking at 15 minutes. So again, you really need to focus on what OSHA is saying, not so much with what ACGIH is going to be saying. But again, you want to protect your workers, and ACGIH is going to give you standards that are going to be more conservative, but maybe better for your workers in the long run. So another takeaway is that you can exceed 85, 90 decibels, but you do need to remember that these are time-weighted averages. They're not hard and set limits. They are time-weighted averages. So with an 8-hour shift or a 10-hour shift, you need to be below 90 decibels when you do your total calculations. It's one of the reasons that dosimeters are so nice, because you can have a worker working in an environment for a period of time and you have a really good idea of what their total exposure is based on their total shift. So if a worker is going to work for less than 8 hours, they can be exposed to higher decibels, and that's certainly something that you want to keep in mind. So slide 34 is a summary of occupational noise regulations. So again, you see with OSHA, you have a lot of different numbers that are kind of getting bounced around here, but the main thing to remember is, essentially, if you're working in any given area with regard to acoustical requirements, that these are the things that you should take into consideration, that you're generally going to be at column C, which is 90 decibels in accordance with federal EPA or federal OSHA standards. That's 90 decibels for federal OSHA. On to slide 35, summary of occupational noise regulations in the United States. So you see this with train workers, Department of Transportation, Department of Defense, that they have some different standards associated with what they're going to be exposed to. And these are the noise regulations for each of these groups. But again, these are really more for edification if you wanted to look at these, not something I'm going to be testing you on. So on to slide 36, sound level surveys. You have area measurements, equipment source measurements, exposure durations. These are all very important to understand when you're taking surveys. You want to survey the area, you want to survey specific equipment, and you want to understand exposure durations. So OSHA permissible exposure levels and ACGIH, where are you on this? You really focus on that OSHA permissible exposure level. So you go out to these areas, you do a survey, and you want to make sure that you understand the time-weighted averages associated with your workers' exposure to these noises. Slide 37. This is calculating dose with the time-weighted average. Pretty straightforward. So your dose is essentially going to be C1 over T1 plus C2 over T2, so on and so forth, where C is the employee's exposure time at different noise levels, and T is the total time allowed at that noise level. So this is going to be based on OSHA's PEL. So federal standard again is 90 decibels. And really, so California is 85 decibels. I kind of want you to just roughly understand that. So if you're going to calculate a dose and time-weighted average, this is what you would use to do that. Slide 38 is commonly used octave bands, which is really something. Let's just go ahead and skip over that. Slide 39 is a sample data sheet, and this allows you to record information for your workers. If you are a manager, this is something that you will do if you work in a very noisy environment. If you don't work in like a manufacturing, it's something that you rarely do. But again, it gives you a chance to take a look at the form. Slide 40 is classes of noise exposure. So you have continuous, impulsive, and impact. Continuous is going to be intervals less than 1 second, so it's a non-stop sound, basically like running a printing press or something like that. Impulsive is going to be less than 200 impulses per second. So this would be things like pneumatic hammers and rivet guns and things like that. And then you have impact, which is a duration of less than 1 second and an interval of less than 1 second. So this would be something that is um, going to be fairly noisy, but not the same level as continuous, where continuous is going to be a non-stop sound, and impulsive is a little bit different as well. But again, continuous is really what you're going to be focusing on. But when you think about like impact, you're thinking about maybe like an explosion, possibly just a loud sound that doesn't happen all that often, but certainly is something that can have an impact on your hearing. On to slide 41 with noise control. So if you have sources like dampers, enclosures, mounts, and fans, these are going to be sources for noise control. And your noise path is going to be like an acoustical tile, floor tile, or a greater distance, or barriers that may be impacting sound and noise control. And then you're going to have the individual that is going to have an enclosure possibly around them, or personal protective equipment like earplugs or the larger ear protection devices. So noise control really focuses on how can you utilize sources, how can you utilize the noise path and the individual to control noise as best as possible. On to slide 42. This is control measures, so you can certainly utilize engineering, administrative, and personal hearing protection to make sure that people are well protected from excessive noise. Engineering, you can build in walls that will protect people from large noise sources. You can also utilize administration by making sure that people are only exposed to these for a brief period of time, or within the limits of the time-weighted average. And then personal hearing protection, which is again very important for control measures. On to slide 43. This is a glass shield, so you can see before and after how substantial this is actually going to have an effect in regard to noise pressure levels for the decibels and the octave bands. So you see that there was a big shift in this at right around 500 hertz. And that's where that started to occur, and with the glass shield, you notice that it really begins to fall off at 500 hertz. So slide 44 is an example of general acoustic performance, ducts and mufflers. So these are things that can have a very positive effect in regard to noise reduction. Slide 45 is noise levels with and without mufflers. So obviously you see a huge difference here, and you know how this, you're very familiar with this process if a vehicle is driving without a muffler, how extraordinarily loud it is. Slide 46 is types of hearing protection, and you can take a look at these. There are semi-insert earplugs, there are standard earplugs, molded, earmuffs, and even helmets as well that can protect your hearing. Slide 47, noise reduction ratio is a way of gauging effectiveness of a piece of equipment, and there's an example here. So if you move on to slide 48, this is going to give you a noise reduction ratio question, which is that you're at Coachella and you're listening to Beyonce at 100 decibels. You have earplugs that have a noise reduction of 33 decibels. So what's your effective exposure once you put in the earplugs? And if you move to slide 49, it's going to give you the calculation for that. So obviously you cannot just subtract it, because this is a logarithmic scale, right? This is a log scale. So if you go down to the correct method for calculation, you're going to have the proper way of doing that calculation. And I encourage you to take a look at that and just kind of run through it so that you know how to do it. But again, not something that is going to be, I'm not going to have you do like 10 of these, but certainly something that can be useful to you if you are trying to figure out whether or not this is going to be an acceptable noise reduction regime for your operation. Slide 50 is a hearing conservation program, and this is kind of important because this gives you something that you can do if you're working in a built environment, if you're working for an organization as a manager. This is going to be something that you might have to do if you work in a very noisy environment. So a hearing conservation program is required when your exposure exceeds your 8-hour time-weighted average of 85 decibels, which is the action level. So the components of the hearing conservation program are going to include monitoring, where you're actually using noise monitoring devices like dosimeters, audiometric examinations for your staff. So you're going to medically monitor the staff to make sure that they're not experiencing temporary threshold shifts or permanent threshold shifts. Hearing protective equipment that you're going to supply for them, a training program on how to use them and how to manage and keep themselves safe, and then adequate record keeping. This is a huge part of this. You have to keep records and make sure that your staff are safe. On to slide 51. Here's an FYI of 80 decibels time-weighted average in 8 hours is also referred to as the action level for OSHA. So again, especially with Cal OSHA at 85 decibels, when you get to this level, you have to start protecting your workers, and you want to have a hearing conservation program at that point if you have workers that are exceeding the action level. On to slide 52. Audiometry is performed by a licensed or certified audiologist, physician, certified technicians, and it has to be done in a suitable testing environment with well-calibrated equipment. So they're going to do a baseline reading within the first 6 months of an individual taking employment, and then they're also going to do annual audiograms for these individuals to make sure that their hearing is being protected. Slide 53 is the annual process, which is looking for standard threshold shifts. So again, as we had mentioned, there's temporary threshold shifts like the ringing in your ears after a concert. It's going to go away, but you also have permanent threshold shifts that, for long-term exposure, chronic exposure, it's not going to heal. So they do this for standard threshold shifts at 10 decibels, at 2,000, 3,000, and 4,000 hertz, and then they retest usually within 30 days. And then they're going to have a baseline to see where you are. And certainly an organization wants to make sure that you don't have pre-existing hearing damage if you're coming into a noisy work environment. Slide 54, when is hearing protection required? And this again, this is a very tricky question. So really the goal is to provide hearing protection when the action level is exceeded. So as you remember, that's 85 decibels, which is less than a lawnmower with an operator. So that is going to be the action level, just to kind of give you a rough idea. So the employer has to enforce the use of hearing protection when the exposure exceeds 90 decibels or the criteria for the standard threshold shift is met at less than or greater than 10 decibel shift. So a lot of employers like UC San Diego require the use of hearing protection when the action level is exceeded, and certainly that's a really good idea. Err on the side of precaution with your staff. Protect their hearing as best as you can, and that's always going to be a good idea. On to slide 55. Hearing protectors is continued. Employer must provide a variety of protectors, training, and supervise the correct use. So it really is the manager's responsibility to provide multiple types of hearing protection and also the training so that individuals know how to use them. But they also need to kind of follow up and just watch them and make sure they're actually using these things. Slide 56, which is a training program, has to be repeated annually. Should be for all employees that are exposed above the action level at 85 decibels. Employees informed of the following: that effects of noise on hearing can be detrimental. They need to be made aware of audiometric testing and procedures, and they also need to be made aware of the various hearing protectors that can be used, including the instructions for care and fit and use. Slide 57 is record keeping. Again, this is very vital. If you become a manager, you really have to have good records, and this can include the pre-employment hearing tests, and should include these things, because the goal is to make sure that if someone has hearing loss and then they experience hearing loss on the job, how much of that was pre-existing before they began employment at your facility. And that record keeping component is very, very important. Slide 58 has some good references that you can check out. It has a little bit of information on noise that you can check it out. And that's it for this video. I'm going to do another short video here coming up that is going to have some information for you in regard to your lab. So be on the lookout for that. It's going to come here shortly.